Alright, why are we jumping into Chapter 19 at this particular juncture in our OChem adventure? Well, the reason why is because there are some really useful reactions that will help you throughout the rest of the semester and bring back some useful concepts from what we've already learned. So that's why we're going to do it. It's really all about synthesis. So this is the great big gory outline of Chapter 19, but we are only going to focus on two things, the very beginning and the very end. And as you read through the textbook, keep in mind that there are several references to reactions we have not yet learned. So don't worry about that. Just keep in mind the fundamental concepts that I'm going to present in this mini lecture, and we'll be cool. Then when we get to those reactions later, it will all make much more sense. Okay, really what Chapter 19 is about and why we're looking at it now is because it's about synthesis, which is making new molecules. And making new molecules is a pretty big deal in, well, on the globe, period. Here's a couple of examples. They're kind of smallish examples. But for example, this molecule over here on the left. This guy? AZD. This AZD guy, it's pretty small molecule. It's made from two very, pretty simple pieces. But it's in the second phase of clinical trials as a treatment for solid tumors. So it's a useful and important molecule. Then there's this crazy mess. The synthetic target that we're focusing in on is this crazy thing down here. Quite wild. But if you look at it, you'll see there are two double bonds here. And because of those double bonds, these researchers have built this molecule as a molecular switch that can change conformation when it's hit by light, changing from the EE to the EZ or the ZZ, and that molecule's change in conformation allows it to do special things like act like a switch. So a lot of promise for using that in all kinds of applications. So synthesis in terms of making new molecules has really broad applications, from medicinal uses to photovoltaics to you name it. So that's why it's important. What is this Umpolung stuff? Well, Umpolung's a fancy German word for a pretty straightforward concept, and it has to do with the fact that we know our electrophiles and nucleophiles, and we know that if I try to react an electrophile with an electrophile, it's not going to work. It's no reaction. So here are my two electrophiles. Let's say I would really like to make this molecule. And clearly, what I can see is I'm trying to add this piece to this piece. And if that's the case, it seems like I just want to go root and here and to something like that, making a new bond between this carbon and this carbon. But wait, that's an electrophile, as we know, because there's a delta positive on the carbon. And while we haven't studied these carbonyls yet in any kind of gory detail, we certainly know from Chapter 2 that that is a very polar bond. Therefore, that carbon has a delta positive, and delta positive plus delta positive means they're not interested in each other. Therefore, I can't make that like that. However, Umpolung basically means I can reverse the reactivity of this alkyl halide. I can change it from an electrophile to a nucleophile. This is a synthesis that we'll learn in Chapter 19, where I make what's called a Grignard reagent, and because of the polarity of the carbon-magnesium bond, I have actually a positive on the magnesium and a delta minus on my carbon, making this a nucleophile. So now this nucleophile can react with that electrophile, and I do get my desired product. An extremely important reaction we will learn a little bit later. The other Umpolung thing that we will learn has to do with this reaction. Now we know enolates are nucleophiles. We know how easy they are to make. But come on now. This carbon nucleophile, the enolate, in this carbon nucleophile, the cyanide anion, they do not want to react with one another because of electron repulsion. But if I convert my nucleophilic alpha carbon by bromination into now an electrophilic alpha carbon, because I put that bromine on there, I have a nice dipole. So now I have an electrophilic alpha carbon. My Cn minus can attack, kick out my leaving group, and there you go. I get the desired product. So that's what Umpolung is. Umpolung is just switching reactivity. Now the other aspect of the introductory material of Chapter 19 is this idea of kind of getting hints from your target molecule. So if you focus on your target, and as you know, I'm always telling you to work backwards from your target, just look at your target and say, what hints can I get from looking at this molecule? And the huge hint that you are going to get from looking at this molecule is that you have functionality on carbons that are right next door to one another. 1, 2. 1,2 functionality is a big hint. So that's telling you that somewhere along the line, it's really very likely that you're going to want to use maybe an alkene or an alkyne, which also has that 1,2 relationship. I'm going to want to use those as one of my starting materials somewhere along the line in these syntheses. So if I see a diol, I should think, I'll make this from an alkene. If I see a dibromide, alkene. How about an alcohol with something else right next door, 1,2, alkene? Because you know what? It might have come from an epoxide. And where did that epoxide come from? An alkene. So 1,2 is a huge hint. Think alkene. Or, again, possibly alkyne. How about this? What big hint can I get from this? Well, it's chemistry that we will learn a little bit later, but the huge hint whenever you see that alcohol, you look at what's attached right here and imagine adding that Y minus as a nucleophile. That can happen readily. You can add Cn minus, you can add the acetylide, you can add enolates. They're all what we like to call the alcohol disconnection. And whenever we see an alcohol from now on, we're going to be thinking, maybe I could make that alcohol from a carbonyl. Finally, here's a hint that we probably should have already been thinking about, and that is, if I have a ketone with something on the alpha carbon, I should be thinking of that thing as being added as an electrophile to my enolate nucleophile. And that works well. I can brominate the enolate. We know we can alkylate the enolate. We will learn that we can add enolates to other carbonyls. We can dehydrate them to get those kinds of molecules. We can add them to alpha-beta unsaturated carbonyls. So all of these reactions, this one, and this one, these are all new. We haven't learned them yet, but these we already know. So when we see this guy as a target, we know we can use enolate chemistry to make it. So focus on the target. You got some big hints by looking at what's there, relationships, etc. And that's the introduction to Chapter 9. Then there's a tragic story, well actually it has a happy ending, about this pet parrot. Gosh, this was an obnoxious bird. And the guy who had the parrot was sick and tired of it squawking all the time. It cursed him out. It was just terrible. It was very offensive. He couldn't even have people over. So finally, he just took the parrot and threw him into the freezer. That's kind of cruel. He wanted to teach him a lesson. So the parrot is in there freezing in the dark, squawking and making all this noise, and finally it just gets really quiet. So the guy's a little nervous. So he opens the freezer door, and the parrot just walks out and looks at him and says, "I am so sorry for offending you. I humbly ask for your forgiveness." The man's a little taken aback, of course, and he says, "Well, thank you. I forgive you." And the parrot says, "Look, if you don't mind asking, what did the chicken do?" All right, and that's all for the intro to chapter 19.